Next, we have Dr. Liu from NTU School of Computer Science and Engineering. He will be sharing his thoughts on his presentation topic, which is contribution aware federated learning for smart healthcare. It will be a pre-recorded session, and then he will be available after that through Zoom for any Q&As.
Hi, good afternoon, everyone. It is my honor to be here today presenting our work on federated learning. I'm going to introduce to you CARE-FL, a contribution aware federated learning for smart healthcare. This is a FL framework with a new perspective, contribution. It also has won the 2022 IIII Innovative Application Award for this work. And as you can see, this is a collaboration among multiple partners, both from academic and industry. We have NTU, WeBank, and EduCloud, and Tsinghua University, and Hong Kong University of Science and Technology. And before we go into the details, I want to introduce you something about me. And my name is Liu Zelei, and I received my PhD in computer science from Jilin University in 2019. And from October of 2019, I have been a research fellow at SCSC NTU under Professor Yuhan's supervision. And my research interest is incentive mechanism design for federated learning and fairness in ethical AI. And first, an overview of our CARE-FL. We proposed the CARE-FL framework, which is centered on contribution information of federated learning. It consists of 3 tiers. The first is the FL infrastructure tier, and which consists of both online FL server, which means currently training an FL module, and the offline FL server, which means continuing previously trained FL models. And the second is contribution evaluation tier, and the third is user interaction tier. This is the 3 main parts of our CARE-FL system. And the CARE-FL framework supports the federated learning model training under a server-based horizontal federated learning settings, which means the participants are from the same domain and their data sets have large overlaps in the feature space, but little overlap in the sample space. This is the CARE-FL targeting tool. In comparing the existing FL-empowered smart healthcare frameworks, so our CARE-FL offers a unique and new capabilities with regarding to the contribution, which can support more sophisticated use cases. And I will elaborate on this in the following presentation. And to the best of our knowledge, it is the first contribution-aware federated learning has been successfully deployed in the healthcare industry settings. Before we head into the details of our CARE-FL, I think it will be better for me to give you some background knowledge about our collaborators and their platform. First of all, EduCloud is a healthcare big data platform. It offers smart healthcare solutions with AI technologies. It provides federated model training services to help healthcare customers such as hospitals, pharmaceuticals, and biotech, and medical device companies, also with some research institutions and insurers to build the required AI models. And its FL service provision framework is based on the open source federated AI technology enabler, or FIG in short, platform developed by VBank. And our work, the CareFL framework, is added on top of this already existing collaborations framework infrastructure to provide functionalities related to and derived from the federated learning participants' contribution evaluations. And for the Edu Cloud, with the new FL platform, the Edu Cloud supports diverse collaborations among different entities. And these collaborations can be lightweight collaborations just between the researchers with their existing data. These researchers often to be doctors from different hospitals. And the second is collaborations between hospitals. And this sort of collaborations may require more quantity of the data site resides in their own site. And the third one is drug developing and analysis research offered by pharmaceutical companies, or maybe even insurers that have commissioned for hospitals to collaboration together to produce an AI model. The same goes to the pharmaceutical companies. Well, such a framework is very helpful for supporting the first stage, which is the supporting privacy-preserving collaborative model trainings. But there are still factors holding the data owners back from participating in it. This is the question or problem the Edu Cloud has been encountered with their promotion of their business models, which is because the different stakeholders involved in this healthcare ecosystem may have additional needs on top of just training and useful FL models. One of the key concerns of the data owners is how to quantify its contribution. For example, a pharmaceutical company may wish to build a model to facilitate drug research by leveraging data from multiple hospitals through federated learning. In order to compensate for the participating hospitals, the pharmaceutical company may need to offer some incentives payouts, right? How to fairly allocate these compensations? I think this is the key question. And the most straightforward idea, well, is to compensate everyone based on their contributions to the final outcome, right? But then the question has become from the how to fairly allocate the compensations to how to calculate the contributions in a fair and explainable manners to the non-specialist in AI field, right? For others outside AI field, to how to calculate these contributions in a fair and explainable manner is the key question. So, with this concern has led us to collaborate with the Edu Cloud, and we have designed for this concerns or for this purpose designed the first AI engine of our CareFL, which has been focusing on the contribution evaluation. The first AI engine is a fast and accurate contribution evaluation. It is incorporated with our proposed GTG Sharply approach, which can evaluate fair and accurate FL participant contribution in a highly efficient manner, which is very important. I will elaborate in the following slides. Well, in order to attract and retain high-quality data owners to federated learning, so fairness is one importance throughout the whole contribution evaluation process. So the FAL participants' contributions needs to be fairly evaluated. And the situation of the federation is often very complicated, as shown on slides. The classic first is the classic data heterogeneity issues due to the non-IID statistical data distributions across the data silos belongs to different healthcare institutions, which can be the quantity, label quality, or the quality of the data. And the second is the data quality of different institutions are different. And this is because the raw healthcare data are often scattered and unstructured and non-standardized. And often it depends on the medical workers to label it or to structure the healthcare data, which affected the quality of the healthcare data immensely for the human interaction. And however, it is not an easy task to evaluate the participants' contribution because under the federated learning paradigms, to protect the data owner's privacy, the federated learning paradigm does not allow direct access to each participant's local data by others, right? No one can have direct access of the data owner's data, so no direct assessment of its quality. The contribution evaluation steps must be performed without expecting the original data. All we can have access to, instead of the direct access of the original data, we can only access to the model performance of the produced model. And this is all we have to calculate the contributions of each participant. So there comes the Shapley value, which is very useful too. Shapley value is a classic approach to quantify the contribution of individuals within the group under the cooperative game theory. And it utilizes each participant's contribution to the utility of all possible subset groups it belongs, and assigns a unique value to each participant. And this makes it suitable as a fair contribution evaluation principle for federated learning. Well, it may be a little bit confusing, so we take this as an example to tell you how and Shapley value works. And here we provide an example. A, B, C works together in a project worth 100 points. And so how many points should each of them get? And based on the given utility evaluation functions V, this is the utility evaluation function V. And we have the utility of A standalone is 10 points, which means if A works on this project alone, the outcome of A's work will be 10 points. And same goes to VB equals to 20, which means B works alone and get an outcome of 20 points. So C gets 30 points. And VAB equals 60, which means A and B works together at this point, and they will have produced an outcome of 60 points. And same goes to BC 50 points and AC is 65 points. And finally, ABC works all together, and this project, it will get 100 points in return. And the next step is how to, with this knowledge, how to fairly assess each and everyone's contributions in this cooperation. So this is what we do. We enumerate all the possible permutations in this cooperation and calculate each one's marginal contribution for the correlation. and average them all together. So take this as an example. This permutation is B, C, A, which means B first comes into the group, and then C joins in, and then A joins in. So with this joining sequence, B will look up here, B standalone will only produce 20 points, which shows right here, 20 points. This is B's value, B's utility in this permutation, 20 points. And then C comes in, and we can see BC comes together is 50 points altogether. And minus the 20 points which B brings in before C comes in, then it's 30 points. And this 30 points is the marginal contribution of C, which gives C 30 points right here. And we know ABC works all together is 100 points. And here is A takes the remaining 50 points. And another example is CAB. And C stands alone, its utility is 30 points. You see right here, C is 30 points. And we can see AC, which is 65 points, which gives a marginal contribution of 35 points, right? 65 minus 30 is out right here, is 35 points. And then B comes along, ABC is 100 points, is minus 35 is the remaining 35 gives to B. And we enumerate all the possible permutations and calculating every participant's marginal contribution in this permutation and average them all together. Average them with all the marginal contributions in every permutation and take an average. And this is the contributions, the final contributions of each participant. A equals to 32.5, B equals to 30, and C equals to 37.5. And this is the this is a fire minor, and also it's an expendable minor, as you can see, without extra knowledge of AI and anything else. So it is easy to use and easy to explain. You can see the Shapley value. It's very useful tool. And therefore, we adopting the Shapley value in federated learning. And here is the normal process of a federated learning training. First, we have a federated model. This is the first round, and we distributed this general model to each data owners. This database represents data owner. And the data owner uses the federated model, trained on the federated model, and they produced a local model of their own. And minus using the federated model and the updated local model, they can have a local grading, right? And each data owners then uploaded its updated gradients to the central server. And we have an updated version of the federated model. We can use fed average to aggregate this, or maybe anything else. And then we distributed this updated version model to the data owners again. And they produced the next updated version of the local model and the next version of the updated grading. Then they upload it again. And we repeat this process until the federated model is converged. This is the normal federated learning process, right? So for adopting the Shapley value calculation directly into the federated learning scenarios will be something like this. First, we have the federated model from the starting point, and then we have all the permutations of the participants joining in together. Let's say this is the participant green, to stand alone, and with the federated model to produce the standalone green model. And this is the participant green and red. And with the whole process, it will produce green and red together model, and repeat this process with all the permutations, right? Until the last, with all the participants joining together, and with the federated model will produce all participants model. And with all the models and their performances, we can calculate the Shapley value of each participant. And yeah, as you can see, this has some big drawbacks of the Shapley values, preventing it from directly be applied to the federated learning, as we can derive from the previous examples, right? The problem is the traditional Shapley value requires retraining of the FL submodels when it requires the utility of the subset. When it requires the utility of subset S, it requires the reproduced model of the subset S. And in the traditional sense, which means we have a federated model and the data subset S, and training a whole new model with the subset data, and then produce a subset model, and then we get the utility of this subset. And we have to going through this the nth power of 2, the FL submodels utility evaluations, which leads to computational overhead when the numbers of the participants rise. And so this is major drawbacks. And our solution is, our answer to that the problem is GTG Shapley, which is a guided truncation gradient Shapley. In short, it's GTG Shapley. It is a fair, efficient, and privacy-preserving algorithm. The CareFL AI engine is incorporated with this our proposed GTG Shapley approach. And the key idea, the first one is that we use model reconstruction instead of model retraining. The idea of a model reconstruction has been shown right here. When we request to evaluate model S, we actually, instead of retraining the model S, we just using the gradient updates to reconstruct, to approximate the model S, and then evaluation its performance. I can show you in the following image, right? Yeah, right here, model reconstruction. Yeah. So we do the model reconstruction like this. In one round of the federated learning, when the local data owners have produced the updated gradients, then these updated gradients have been uploaded to the central server, right? We have all the updated gradients. And what we do is we evaluated, for this round, we evaluated the contributions of each participant. We have each participant's updated gradient, and then we use the traditional Shapley value to produce to evaluate their utility. So if we want the green model, the standalone green model, we just use the updated, we just use the federated model plus the updated gradients, and we produce the standalone green models. If we want to have the orange and the blue utilities, we just use the federated model plus the orange and the blue gradients, plus them together, and generate these submodels. And we do this. This is much easier than retraining the whole subset to produce a simple model to evaluating the utilities. And with the evaluated utilities, we can calculate their Shapley values, hence their contributions. And this is for just one round. And we can do the same thing for the next round. And with each round calculation of their Shapley values, we can just simply add them together to get the final results. And this is our answers to the problem of model retraining, which is model reconstruction. And the second idea is truncating the unnecessary submodels, or the submodel or the subset utility evaluations. Instead of the nth power of 2 submodels or evaluation, we will using Monte Carlo truncations just to evaluate those which are needed for the Shapley values to be calculated. And there are some subsets, their contribution, marginal contribution, or their performance is so insignificant that it won't that much affect the final outcomes. And to evaluating their utilities maybe is a waste of time. This is a trade-off between efficiency and accuracy. And with the Monte Carlo truncations, we can reduce or promoting, improving the efficiency much more, and with just a little bit of drawbacks on the accuracy. And same process, with the same process of the model reconstruction. And there we have been evaluating our GTG Shapley's performance with, we have done empirical studies on 7 existing Shapley value. This has been means Shapley value based FL participant contribution evaluation approach, and they're both IID and non-IID settings. And the GTG Shapley consistently achieved the highest efficiency and accuracy under both IID and non-IID settings. The result is right here. This has been presented in the log-10 scale. So we can see right here, this is GTG Shapley, our proposed method. And for the efficiency, which right here is the duration, you can see this is almost 100 times faster than the traditional Shapley value calculation method, which is retraining the subset to produce a model. And we are almost 10 times faster than the next best performance state-of-art method, almost 10 times faster. And the same thing goes to the non-IID settings. The duration is almost 100 times faster, and for the next best thing is almost 10 times faster. And also, under both IID and non-IID settings, the GTG Shapley also achieves the best accuracy, which is in the log-10 scale, which is very small, very accurate. Yeah, with the knowledge of every participant's contribution in each round calculated, as we can see in the GTG Shapley calculation, we have an idea, and we design the second engine of CARE-FL, which are the contribution-aware FL model aggregation. The CARE-FL provides a novel FL aggregation approach, which selects the best performing submodels in each round from Shapley to be distributed to the FL participants for the next round of local training. And yeah, this is the basic idea of the second engine. What it means is that during the course of contribution evaluation, right, we have even though we have reduced the number from the power of 2 to significant small, but we still calculated during the course of the contribution evaluation, we still produced the performance of different FL submodels aggregate using the local updates from different combinations of the selected FL participants calculated as a byproduct, right? Instead of calculating Shapley value, they just resides right there. And we want to make better use of these submodels. So the contribution evaluation server can identify the submodels with the best performance as the best subset. The subset with the best performance as the best subset FL model. And this information is used to guide online FL server to improve the final FL model performance. What it means is the online FL model it trains the FL model. During the process, it calculating the contributions during the training process. And with the contribution calculations, we can identify the best performing subset as the best set. And with this best set, we can get the best sets corresponding best subset models. And instead of distributing the full participant models, we can just distributing this best subset models, which can also be the full participant models, to each participants or to each data owners. To use this as for the next round of FL trainings. And the reason we take this best subset approach instead of just adjusting the weights of the updated models is like modifying the Fed average weights of, instead of just using the quantity of the data set, we can somehow use the Shapley values. The reason we don't do that, instead of we still using the best subset approach, is because that the relationships between the participants are complicated. The model aggregation is a correlation game, which requires consider multi-wise influence among the collaborators. Sometimes maybe a participant will possess some rare samples or rare data, which can give him a small updated gradient directions, or different gradient update directions from everybody else. Maybe it has a small quantity of the data, and it steps into the error surface. The gradient steps into the error surface different from everyone else with just a small steps, but it's important small steps. If we are boosting the small steps based on its contribution to the whole group, we are amplifying by its contribution, which may hurt the final outcome of the aggregated model. So we want to remain the weight of each updated gradients. So we just want to select out this best subset. Therefore, we take the existing best performance correlations directly. And we have conducted an empirical studies of this CARE-FL model aggregations on public benchmarks, CIFAR-10 datasets, both under IID and non-IID settings, comparing to the Fed average approach. And we can see right here, both under the IID and non-IID cases, the blue line is our CARE-FL aggregations, the yellow line is the Fed average aggregation. The blue line is outperforming the yellow line, especially in non-IID settings, which quite suitable for the our collaborations with the smart healthcare scenarios. And in the following, I will be presenting some details of our CareFL framework. And the GTG sharply only requires a list of unique participants' IDs, which can also be a mask ID, just a unique ID is fine. And computes the participant's contribution in an efficient manner and returns the result to the FL server. And in addition, they also identify, it means the CareFL server, the contribution evaluation server. It also identifies the best subset and passes this information to the FL server to improve the model aggregation. And it worth mentioning that the aggregation function is only relevant for the online FL training, during which the global FL model is still in the process of being established. Yeah. This is the... And then I will presenting the detailed interactions during the which the contribution evaluation server or the CE server workflow, the workflow of the CE server. Even though the same evaluation algorithm is used for both online and offline modes, and most of our CareFL framework, the interaction process are slightly different. I will take online mode as an example. The evaluation process is as follows. There are three types of entities. The first is the federated learning FL server, which is right here. And the second is the FL participant, which is the data owner. And the third is the contribution evaluation server. And first step is the FL server will initiate an FL session under the FATE framework. This is done by sending a homomorphic encryptions key to the FL participant. And then FL server sends the masked ID of the FL participants joining the current round of training to the CE server. And the third step is the CE server sends the combination of participant IDs selected by the proposed GTG Sharpie algorithms, the selected ID or the subset ID to the FL server for Sharpie value-based contribution evaluation, sending back IDs. And the evaluation, the submodel evaluation will be done on the FL server to increase the privacy, preserving calculations, verifications. And then the FL server will reconstruct an FL submodel with only the model updates from the set of participants selected by the IC servers. And and then it evaluates the performance of the submodels and sends the results to the CE servers. And the CE servers only receive the result. It won't receive any models or any grading updates to further increase the privacy preserving ability. And the CE server analyzes the received results based on the participants and based on the already at hand information, and adjusts the selected participant set. And then the CE server will produce the new set of participants are sent to the FL server and to be evaluated. And the eighth step is when the CE server determines that enough information has been gathered, and it will stop further submodel evaluations. And then it will calculate the contribution values of each participant. And after the calculation, the contribution values of the participants involved will be sent to the FL servers. And the FL servers will be proceeded to the next round of training. This is the workflow of one round, the contribution evaluation, plus the best subset, the model aggregations as well. And our CareFL framework has been deployed in Edu Cloud technological companies since the March of 2021 in 2 lines of their business. The first is the clinical research service, and the second is real-world trial research services. And both services requires data which need to be collected by hospitals over months or even years under their respective institutional review board supervision. And so far, the CareFL has been used to help 8 well-known medical institutions in China to train AI models for risk predictions, disease diagnosis, and influence factor analysis scenarios. And there are 3 cases. The first is leukemia, and it is clinical research for recurrence risk prediction after stem cell transplantations for acute leukemia treatment. A total of 62,000 patients were included in this study, and 2,830 samples are included after acute leukemia screening and stem cell transplantations. And the second case is biopsy. It is a real-world trial for analyzing major factors influencing a prostate biopsy positivity. And a total of 5,978 patients who underwent prostate cancer biopsy during a 5-year period were screened, and 2,426 patients are selected in this case. And the third case is pneumonia, a real-world trial for classifying whether hospitalized pneumonia patients will be transferred to the intensive care unit or ICU or pass away. And a total of 103,455 sample data was selected based on hospitalizations, deaths, and transfer to ICU for continued treatment during the hospitalization. This is the detailed information of 3 cases, and this is our result. And in Edu Cloud in the business, we have used a logistic regression model and a homoscedastic tree models have been trained with fat average in the previous systems, and later retrained with our CareFL systems after its deployment. And you can see with the help of CareFL, Edu Cloud has avoided problems of high computational cost and the low accuracy of existing FL participant contribution evaluation process, of course. And this capability not only allows to provide more detailed analysis about the value of each FL participant can bring into building any given FL model without exposing their sensitive data, but also enables a new contribution-aware FL model aggregation approach to be developed. And we can see right here, overall the FL is around 3 times faster than the best performing baseline in terms of evaluating participants' contributions. And it has improved an average accuracy of FL model trained by Edu Cloud by 2.62% comparing to its previous systems, and which is significant in the industrial smart healthcare settings. And we can see with different models and different data sets or different use cases. You can see right here, which means the models and the size is rather non-ID in this sense. So our CareFL has a higher, better performance case. And yeah, this is our deployment results. And next, I will demonstrate the user interface through which the CareFL visualize the FL participant contribution evaluation for the system administrators. And it is, yeah. it is right here. As you can see, it has as you can see, the left sidebar, it has enable switching between three perspectives. The first perspective is federations, and the second perspective is participants, and the third is topics, called topics. I will introduce explain the first functions perspective, the federation perspective. As you can see on the left side, this is the detail, the short information about different federations, illustrate different federations as a applicable card with a brief overview information, such as the federation names and the federation task descriptions in short, and the creation dates and the number of participants right here, and the model performance, the final model performance right here. And when clicking on this on one card, we can see on the right hand side, it will give you a more detailed information about this federation. You can also see the federation name, the creation date, number of participants, and the topic, which means it belongs to leukemia right here, these federations, and give you a detailed description of these tasks. And on this side right here, on the right side right here, this is the overall contributions of all the 8 participants. We can see participant number 3 has the highest contributions in these federations right here. And participant number 4 has the lowest contribution right here. And below them is the information of the model accuracy and the loss in each round. You can see right here, when we move the mouse on each dot, it will give you a detailed information right here. Yeah. And moving down underneath them, this is a grid heat map of the more detailed information about the contribution evaluations about it. Each column is a training round. Each column represents a training round, and we can see on and each cell representing during this round a subset utility of a subset, right? And the FL model consisting of all participants' model updates are highlighted with a white dot or black dot right here. You can see this white dot cell representing participants with all the participants from 0 to 7 with the accuracy of 0.888, and this is a full model is true, right here. And in each column, the submodels of this round is arranged in descending models. Descending matters by the submodel's performance. And when clicking on the cell, the box will pop up with more detailed information about the model's performance and the IDs of the participants involved in these submodels of this round. And lastly, at the bottom, this is the marginal gains of each round or marginal contribution of each round evaluation display on the left. And when clicking on the round's marginal contribution right here, it will show a detailed information of each participant's contributions right here. You can see sometimes there are negative contributions, which means the participants' model updates have a negative impact on the final outcome. For this right here, this is round 8, so we should select participant number 3, 4, and 6 only for aggregated the model for participating in the next round, right? We can eliminate the negative informations right here. Yeah, this is one round right here. So different round has a different information. Yeah, and for the participants' perspective, we can see right here. This is the detailed information of a participant's contribution. It can be ranked, this is a ranking system, it can be ranked on the overall contributions. All participants can be ranked by their contributions under different tasks or different perspectives. Under leukemia, we can see participant number 5 is more specialized in leukemia right here. And for cancers, we can see participant number 4 is more specialized in treating cancers. This data has a higher quality in this cancer research. And for pneumonia, you can see participant number 3 and 7, and participant number 1 has a higher contributions in them. Yeah. And for the topics perspective, we can see right here, we can see different participants, and it's specialties in the different topics. You can see this is the light blue is the overall, and this is leukemia, cancer, and then pneumonia. You can see participant 1 is pretty average and has a higher quality on pretty much every topics. And we can see this right here, participant 4 has a very high specialties in the cancer research, and has very low quality data on the pneumonia research. Yeah, the same thing goes to the participant number 8 has very low quality in the cancer research and very high quality in the pneumonia research. And this gave the federated learning perspective administrators a very nice, wholesome perspectives on the specialties of different participation. So therefore, when a new federation specialized on this topic is asked to be built, as an administrator, he knows how to who to contact and who not to contact, based on this performance right here. And we can inform the hospitals regarding hospitals, they can improving on their maybe data treatment on the corresponding topics with low qualities as well. Yeah. And this work has also been awarded the AAA Innovative Application Award as well. And well, this is the end of my presentation, and thank you for listening. Thank you.
I see part of the code, your workflow inside there, you have a HE key, right? You have a HE key that you set from within your workflow.
Location what?
Your homomorphic encryption key that you send from your FL server to your FL participant. Your workflow.
Contributions.
Yeah, your contribution. You have sent a HE key from your FL server to your FL participant.
Oh, encryption key, right?
Yes, encryption key. Yeah.
Right.
So that one is your HE, which means that you're using Palas, you're using public key.
I'm sorry.
Are you using a public key for a HE? That's the thing.
Sorry, the sound is very muffling, so.
Okay, I go slow. You send an encryption key over from your FL server to your FL participant. Correct?
Yeah.
Yes.
Right.
The encryption key, it is a public key or is a shared key?
Oh, this is handled by the FATE frameworks. It's already done by the already developed open source frameworks. So all the contribution evaluation server need is not any encryption keys, because we don't want to risk handling or touching having access to the data, even though it's encrypted data. So all the contribution evaluation server need is a mask ID, a unique mask ID of each participant that we can identify them in the coalition. So that's basically the information they need, and also the utility or the performance of the SAM models is what the contribution evaluation server need. and it's the focus of our research right here. So our collaboration is not focusing on the details of how to build a federated learning, general federated learning framework, rather than build up on that framework and focusing on the contribution information. Yeah.
Right, because I'm not sure, I'm not too familiar with FIT, the HE keys, what they're using. It doesn't matter. It's okay. Thanks.
Thank you.